Welcome to the deep dive. If you work in a specialized field, and maybe especially if you're in modern medicine, you know this feeling. You are constantly battling just information overload. We live in this age where research is pumping out incredibly powerful computational models, things that could really revolutionize patient care, diagnosis, prediction.
Yeah, but those models, they often just end up trapped, don't they? They need, specialized coding knowledge or maybe proprietary software or just a really steep learning curve to even run them. So they kind of stay locked away in academic
Can
journals.
never make that leap.
Exactly. Never get to a general practitioner's office or, into a patient's hands where they
Yeah.
could actually do some good.
It's such an irony, isn't it? Years of work go into perfecting some algorithm, but maybe zero time is spent thinking about the actual person who needs to use it. And that friction, well, it just kills the utility.
It really does.
So today, we are diving into a potential solution for that exact problem, a prototype called Robodoc. It's been developed by an independent researcher, Jorge Garapierres.
That's right. And we've actually got access to the research paper detailing this system. And it's been quite the journey for this paper, I understand. Apparently a pretty long and rigorous review process, multiple rounds, but it's finally at that preprint stage now,
Yeah.
almost ready for formal publication.
Ah, okay, good to know. So it's pretty much hot off the press, in academic terms anyway.
Basically, yeah. And it's essentially a blueprint for turning these really complex medical diagnostic models. We're talking analyzing chest x-rays for pneumonia, maybe assessing diabetes risk based on lab results, into something much simpler, like just an intuitive conversation with a chatbot.
Okay, so our mission today is really to understand this core architectural shift. How can these large language models, LLMs, the brains behind things like GPT-4, how can they evolve beyond just being general knowledge engines and instead maybe function as an intelligent, shifter or maybe glue?
Yeah, glue is a good word for it.
Making these highly specialized, domain-specific tools accessible just by chatting, we're going to explore the radical benefits, but also the inevitable risks of applying this kind of architecture in health informatics.
Right. Let's unpack this architecture then, because it sounds like a complete reversal of how things are usually done, the traditional UI, UX, and bioinformatics. The problem, like you outlined, is that these specialized models, they force the user to understand the model's own language, its specific syntax input requirements.
Exactly. Imagine a pulmonologist, right? She wants to use the latest computer vision model someone developed for lung nodules. Should she really have to hire a data scientist or, spend 6 weeks learning Python just to get an answer from it?
No, of course not. That's unrealistic.
It is, and that fundamental limitation, that learning curve, it's really what stops these amazing computational models from being used in everyday medicine. It's a systemic barrier to adoption, really.
And this Robodoc prototype, it aims to just remove that barrier entirely. That's the goal. It positions the LLM-powered chatbot as the ultimate user interface, the ultimate user experience, if you like. So instead of dealing with complex APIs or fiddly input fields or maybe some clunky desktop software, you just talk to the AI.
You just chat.
You chat, and it handles all the computational heavy lifting behind the scenes.
Okay, so it simplifies interacting with these complex tools right down to just a natural human conversation.
Pretty much. As Pyers notes in the paper, the user doesn't need to know how the diagnostic model actually works under the hood. They just need to know what result they're trying to get. It's kind of like the next step from graphical user interfaces, replacing buttons and menus with just language.
You mentioned an analogy the author uses, comparing it to Simulink and MATLAB. Now, for a lot of listeners, that might be a distant memory from some engineering course, maybe.
Huh? Yeah, maybe. But it's actually a perfect metaphor for accessibility. Simulink lets engineers who might not be, absolute experts in differential equations, build these incredibly complex mathematical models just by visually connecting boxes on a screen.
Right, dragging and dropping blocks.
Exactly. And the underlying deep math, the equations, that's handled automatically. The LLM here is doing something similar.
Yeah.
It's handling that complex translation between what the human wants, their intent, and the machine's logic.
So the magic, the sort of technological glue holding this together, it's fundamentally built around OpenAI's function calling capability. That's what lets the AI turn language into actual actions.
Precisely. That's the engine. It bridges that natural language layer, the conversation, with the hard computational layer, the specialized models.
Mm-hmm.
And the user is completely unaware of this process happening. It's all deep under the hood.
Okay.
Based on the source material, the LLM performs 3 really critical steps. And it does this based entirely on the user's conversational input.
Okay, break down those 3 steps for us. What's happening there?
All right, so first is intelligent tool selection. The LLM has to figure out dynamically which specialized model or tool, as the paper calls them, it needs to use. So if the user uploads an image file, say a JPG or a PNG, the LLM recognizes the file type and knows, okay, I need to call one of the computer vision models, either the X-ray one or the OCT one.
And if they type text instead?
Well, if the user types in a bunch of physiological measurements in just a text block, like my A1C is 6.5, glucose 120, it knows, this looks like data for the text-based predictive model, like the diabetes risk assessment tool. So it's constantly kind of triaging the user's intent based on the input format.
So it's not just a chatbot, it's acting like a smart router too, deciding where the request needs to go based on, well, the content and the format of what you give it. Okay, what's step 2 then?
Step 2 is, well, arguably the most crucial technical leap here, parameter extraction and formatting. See, these specialized models, they only speak in highly structured data, usually like a clean JSON object or maybe a strict data frame with specific columns.
Right, machines need things neat and tidy.
Exactly. But the user, the human, we speak naturally, sometimes messily. A patient might type something like, I'm a 24-year-old female and my blood sugar was 110 yesterday after breakfast. Oh, and my BMI is 35.42, which I got from my Fitbit, by the way.
Okay, yeah, typical rambling description.
Totally normal. But the LLM has to mine that unstructured text. It needs to pull out 24 for age, 110 for glucose, 35.42 for DMI, and just as importantly, it needs to ignore the irrelevant details like gender, in this model's case, or where the data came from, like the Fitbit comment. And then it has to package just the required data into a clean, machine-readable format for that specific diagnostic model.
And that translation process from, rambling human text into precise machine syntax, that's exactly where older computational interfaces often broke down, right? Because they made the user do that formatting themselves, fill in these specific boxes.
Absolutely. It was tedious and error-prone, so the LLM takes on that burden. And then the third step, that completes the loop, response generation. So once the specialized model runs its calculation and spits out a technical result, maybe a simple classification like bacterial pneumonia, or perhaps a probability score like 0.99 confidence, or a risk percentage for diabetes, the LLM takes that raw, often numerical, data.
Which might not mean much to the average user.
Exactly. It takes that raw data, interprets it, crucially adds the necessary triage information like urgent referral needed or routine checkup recommended, and then crafts a final, friendly, human-like response. It tells the user not just the result, but what they should probably do next, all without needing them to stare at, raw probability scores.
Got it. The source paper makes a clear distinction here. It calls this a task-oriented conversational AI. How does that focus, that philosophy, impact the system's design compared to, say, a general chat tool like ChatGPT?
That's a really important point. In a purely chat-oriented AI, the main goal is often just dialogue, engagement, maybe exploring general knowledge. We sometimes call that general domain conversation. But here, with Robodoc, the conversation is really just the interface.
It's the means to an end.
Precisely. The system is task-oriented because its primary goal, its reason for existing, is to execute specific, real-world diagnostic functions. The LLM's ability to chat is subordinate to its function-calling capabilities. It's there to solve a problem, not just to have conversation.
And this task-oriented focus, it allows for what the author calls the Lego approach to building the system, this idea of modularity.
Yes, and modularity is a fundamental strength of this architecture because the LLM is handling those complex steps, selecting the right tool, extracting parameters, interpreting results. You can add new diagnostic models incrementally, like adding new Lego bricks. You don't have to redesign the core chatbot interface every time.
Ah, okay. So think about it. If tomorrow some researcher perfects a brand new model, maybe for early skin cancer detection from photos.
Right. The development team working on Robodoc wouldn't need to rebuild everything. They primarily need to integrate the API for that new skin cancer model, and then provide the LLM with clear instructions on when to call this new tool, like when the user uploads a skin photo and how to call it, what parameters it needs.
So the existing pneumonia or diabetes modules, they just remain completely untouched.
Exactly. They're independent modules. This enables straightforward, continuous functional expansion. It allows the platform to become this scalable, constantly evolving hub of medical models, as you might think of it. And practically speaking, this drastically lowers the long-term maintenance and integration costs compared to building traditional monolithic software where everything is tangled together.
Okay, now let's pivot to the specific specialized tools that Robodoc is actually managing in this prototype stage. You mentioned 3 diagnostic models, split into those 2 distinct pathways, image-triggered and text-triggered.
Correct. The system is designed to route the user immediately based on their first action. If you upload a file, you trigger the image pathway, which leads to the computer vision models, the X-ray, and the OCT scan analyzers. If you start typing in measurements, like your blood pressure or glucose level, you trigger the text pathway for parameter extraction, and then the predictive models, like the diabetes risk predictor.
Let's start with the image models. The paper notes both the chest X-ray model and the iScan model were built using Google's Teachable machine. And crucially, they leverage transfer learning. We should probably dig into transfer learning a bit, especially since the source mentions its fascinating superiority in terms of efficiency here.
Yeah, transfer learning is a really big deal, especially for getting models built quickly. See, training a massive neural network completely from scratch, that requires huge amounts of data and a lot of time, often weeks, even running on high-end GPUs.
Right, you need thousands, maybe millions of examples.
Typically, yes. But transfer learning lets you take a shortcut. You start with a pre-trained model, in this case, the paper used MobileNet, which is a model already optimized for efficient image recognition on devices like phones. This model has already learned fundamental visual concepts, things like edges, textures, basic shapes, from being trained on massive, generalized data sets like ImageNet.
So the model already understands a sort of basic visual grammar. It knows what lines and curves generally look like.
Exactly. It has that foundational knowledge. So you then only need to retrain the very final layers of the network, the specific classification layers, using your much smaller, specialized medical data set. And the author found that using Teachable Machine, which simplifies this process, and MobileNet as the base, their models converged really fast, sometimes in just minutes.
Minutes. Wow.
Yeah, and sometimes requiring as few as, say, 30 to 50 images per condition they were trying to classify.
That efficiency gain is honestly astonishing. If you put that in historical context, I mean, even 10 years ago, getting high accuracy on specific medical image classifications like this would have absolutely required hundreds, probably thousands of carefully annotated images and days, maybe weeks of dedicated computation time.
It completely changes the game.
Mm-hmm.
It essentially democratizes specialized model development. The speed and the low data requirement is an enormous advantage, especially for independent researchers like PIers or smaller labs. It lets them rapidly prototype and integrate successful academic models into a functional system much, much faster.
Okay, let's detail the first image model then, the chest x-rays. What's it doing?
Right. This model is focused on pneumonia detection. It classifies chest X-ray images into one of 3 categories. First, bacterial pneumonia. This is often acute, needs quick treatment, so it's flagged for an urgent referral, usually for antibiotics.
Okay.
Second, viral pneumonia. This is generally managed differently, often with just supportive care, rest, fluids. So clinically, it represents a less urgent pathway than bacterial. And third, obviously, normal. And crucially, the paper notes the model uses data that replicates findings from well-respected academic research in the field, showing that this architecture can successfully wrap around established medical knowledge, not just invent its own.
Got it. And the second image model. That one addresses specific and potentially very urgent eye conditions using optical coherence tomography scans, OCT scans.
Yes. The OCT model identifies 4 conditions that affect the retina. There's choroidal neovascularization, usually shortened to CNV, then diabetic macular edema, or DME. Third is drusen, and finally, normal. And this area, looking at these eye conditions, really highlights that critical link between just identifying something in an image, the diagnosis, and deciding what needs to happen next, the triage.
Right, what's the triage significance of those specific conditions? Why are they important to distinguish?
Well, CNV involves abnormal blood vessel growth under the retina, and DME involves fluid buildup in the macula, often due to diabetes. Both of these conditions are designated in the system as urgent referrals.
Urgent because?
Because they can lead to rapid and irreversible vision loss if they're not treated pretty much immediately. Time is absolutely critical. Drusen, on the other hand, these are small yellowish lipid deposits under the retina, often associated with age-related macular degeneration. While they need monitoring, they don't usually represent an immediate emergency, so they're classified as a routine referral.
Okay, so the system needs to understand not just what it sees in the OCT scan, but the clinical implication of that classification to route the patient correctly, urgent versus routine.
Exactly. That transition from just image recognition to understanding clinical urgency,
Hmm.
that's part of the LLM's final interpretive task when it crafts the response.
Okay, now let's switch over to the text model, the diabetes risk predictor. Why did the researcher have to shift away from using teachable machine for this particular model?
Right. It's because Teachable Machine, at least in its current form as described in the paper, is primarily built for handling unstructured data,
Mm-hmm.
visuals like images and videos or audio. The diabetes model, however, it needs highly structured quantitative physiological measurements. Things like specific numbers for blood glucose, HbA1c, BMI,
It's not looking at a picture, it's crunching numbers.
precisely. Therefore, the author built this model directly using TensorFlow.js, often abbreviated as TFJS.
And why is the use of TFJS significant here, beyond just being compatible with numerical data?
Well, TFGS is really interesting because it allows machine learning models to run directly within the user's web browser environment using JavaScript or TypeScript. This has potentially massive implications for performance and, maybe even more importantly, for privacy.
How so?
For performance, it can eliminate the server-side lag you sometimes get when a complex prediction model has to run on a remote server and send the result back. The calculation happens right there in your browser.
Yeah.
For privacy, it potentially allows the predictive computation to happen entirely client-side, meaning your sensitive physiological measurements might stay on your own device rather than being transmitted across the internet to a server for processing.
Ah, okay. That makes the system potentially much faster and definitely more privacy preserving, assuming the architecture is set up so the LLM only sends, say, necessary, maybe de-identified parameters upstream just to confirm the function call, but the actual calculation with sensitive data stays local. What inputs does this diabetes model actually need?
It uses 6 specific features that are known to be critical for diabetes risk assessment. There's age, BMI, body mass index, HbA1c level, that's the measure of average blood sugar over about 3 months, the current fasting blood glucose level, and then 2 binary inputs. The presence or absence, coded as 1 or 0, of hypertension, high blood pressure, and the presence or absence of heart disease. The underlying model itself was trained for high accuracy, apparently achieving convergence around 90% in testing.
We talked before about how the LLM has to extract these specific parameters from potentially messy conversational input. Let's make that process a bit more concrete. How is that parameter extraction capability really put to the test?
Yeah, they tested it across several really important scenarios, which are documented in the paper's results. So consider a patient typing something like, I've been feeling really tired lately, I'm 45, and my doctor just told me my A1C is 7.2. I don't have any heart disease, but I do have high blood pressure, and I weigh about 220 pounds. I'm 5'9".
Okay, yeah, that sounds like a pretty common rambling patient description you might hear.
Exactly. So the LLM has to parse all of that. It needs to calculate the BMI from the height and weight first.
Mm.
Then it needs to extract the 4 non-negotiable quantitative features, age 45, A1C 7.2, and the 2 binary features, heart disease, no, so hypertension, yes, so 1. And the testing showed success in 2 key ways here. First, in successfully identifying and filtering out the unnecessary information, like the comment about feeling tired or the raw weight and height which needed conversion.
Right, stripping out the noise.
Yes. And second, perhaps even more importantly, how it handled missing parameters.
Ah, the handling of missing data. That's often the acid test for how intelligent a system really is, isn't it?
Absolutely. Because real-world data is often incomplete.
Right.
So when the user omitted a critical value in their input, let's say they forgot to mention their fasting blood glucose level, the LLM intelligently halted the function call process.
It didn't just guess or assume 0.
No. And that's key. Instead of just running the prediction model with incomplete or, worse, zeroed-out data, which would guarantee a bad, unreliable result, it paused the flow. It then generated a specific targeted question back to the user, something like, okay, thanks for that information. Before I can calculate your diabetes risk, I also need your most recent fasting blood glucose level. Could you please provide that?
That demonstrates a higher level of, well, cognitive ability, doesn't it? Especially in GPT-4's handling of these function calls compared to maybe earlier LLMs. It understands the dependency chain required to actually execute the task properly.
Exactly. It knows what it needs to proceed, and it asks for it. It doesn't just blindly follow instructions with bad input.
Okay. Finally, before we move on from the tech stack, let's talk about the unified development environment. The paper emphasizes that the entire system front-end interface, The ML execution via TFJS and the API integration is all built using Angular and TypeScript. Why is using a unified stack like this so important for a project of this nature?
Well, in any reasonably complex software project, integrating technologies built in different programming languages like, say, having a Python backend for the machine learning, a JavaScript front end for the user interface, maybe a Java component for connecting to some external API, it creates enormous complexity. It's often called DevOps overhead. You need teams with different skill sets, different deployment pipelines, complex interactions between the
It
parts.
gets messy fast.
It really does.
Yeah.
So by choosing Angular, which uses TypeScript, and then integrating the machine learning directly via TensorFlow.js, which also uses JavaScript TypeScript, the entire stack gets unified under basically a single language and framework.
Which means, potentially, the same development team, or at least developers with very similar skill sets, can manage the front-end user experience, the data management logic, and even the machine learning logic implementation.
Precisely. It dramatically simplifies things like debugging, ongoing maintenance, and scaling the application later. Furthermore, the architecture is designed for decoupling, even within this unified stack. The models themselves, the actual trained ML models, the brain, if you will, can be hosted remotely, maybe on a service like Google Cloud, as mentioned, for the teachable machine models. And the Angular application, the chatbot interface, can be deployed somewhere else entirely, like Heroku, as mentioned in the paper, and it simply loads those models via a web link when needed.
So you get separation of concerns. The brain and the app are distinct.
Exactly. This separation allows the teams maybe training new ML models and the teams working on the core chatbot application to operate somewhat independently, which can really accelerate the whole iteration and improvement process.
Okay, so we've established this pretty robust-sounding architecture, but, the true utility of any medical tool, especially when using AI, is really proven in its performance, and maybe more importantly, in its failure modes. We need to understand where it goes wrong. So let's turn to the results from testing the prototype, focusing on the successes, yes, but particularly where those critical behavioral deviations occurred.
Right. Starting with the text pathway, the diabetes prediction model, that actually performed very predictably and successfully according to the paper. When all the necessary parameters were supplied by the user, the model ran correctly, and the LLM produced a clear, conversational result with the calculated risk prediction.
And the key success there, as we discussed, was its intelligent handling of missing data.
Exactly. That ability for the LLM to perform that stopgap measure, pausing and specifically requesting missing information before attempting to execute the prediction function, that was a major positive finding. It behaved reliably in that text-based scenario.
Okay, now for the image pathway. This is where we saw some more concerning triage errors emerge in the testing results. Let's start with the pneumonia model, the one analyzing chest x-rays.
Okay. So on the most urgent cases, the system actually succeeded quite well. When it was presented with an X-ray image clearly showing bacterial pneumonia, it correctly identified it. And critically, it generated a response that correctly scheduled an urgent referral. And it did so with high confidence reported, around 99%.
So for the most dangerous common type, it worked as intended. That's a clear win for patient safety, obviously.
Absolutely. However, the first deviation noted was a significant triage mistake concerning viral pneumonia.
Right. Viral pneumonia, as you said, usually requires supportive care, not necessarily urgent hospitalization like bacterial might.
Correct. And in these cases, the model actually got the classification right. It correctly identified the image as showing viral pneumonia, but it then misjudged the clinical severity, incorrectly setting the subsequent referral action as urgent, same as for bacterial.
So it wasn't a failure of the image recognition model itself.
Not according to the author's interpretation. They frame it as an interpretive failure by the LLM when processing the output of the classification model. The LLM received the signal viral pneumonia from the model, but the rules or the prompt guiding the LLM on how to translate that specific classification into a referral urgency level were apparently not precise enough.
Okay, that suggests maybe the LLM, when given any ambiguity or choice between urgent and non-urgent, perhaps defaults to or errs on the side of caution unless it's explicitly told otherwise in its instructions.
That seems like a very plausible explanation, yes. Which leads to the second deviation reported for the pneumonia model, which was a classification error, this time involving normal cases. The model apparently showed a tendency to misclassify normal, healthy chest x-rays as having pneumonia, sometimes viral, sometimes bacterial.
Okay, that's a false positive.
Exactly. Now, the authors framed this, interestingly, as a safer error. Their reasoning is that, clinically speaking, it's generally preferable to send a healthy person for some unnecessary follow-up testing and over-referral than it is to miss a genuine, potentially life-threatening case of pneumonia in someone who actually has it, a false negative.
That makes sense from a risk management perspective, but
But it absolutely indicates a classification weakness in the model itself. It suggests the model might be overly sensitive, maybe picking up on subtle image features that overlap between normal lungs and early or mild pneumonia. This could possibly stem from differences between the original training data and the specific images used during the testing phase.
right, the classic problem of model generalization. Okay, so the system is maybe a bit too trigger happy on the pneumonia front. Now, shifting to the other image model, the OCT stands for eye conditions. Here, we saw accurate classification reported for CNV, drusen, and normal cases, with appropriate referrals. But there was a really serious error noted with diabetic macular edema, DME.
Yes, this was flagged as the most problematic deviation during testing. As we discussed, DME is an urgent, sight-threatening condition requiring prompt treatment. Yet, during the prototype testing, the system sometimes misclassified this urgent condition and incorrectly routed the patient for a routine referral.
Oof, that's the opposite of a safer error.
Exactly. The paper specifically notes that this particular case, getting DME correctly classified and assigned an urgent referral, actually required several attempts and adjustments during the development and testing process to get it right consistently.
That feels like a fundamental failure of the triage layer, doesn't it? I mean, if the whole point of an AI like this is partly to reduce bottlenecks and provide reliable first contact advice, then confusing an urgent, potentially blinding emergency with a routine appointment slot that might be weeks away, well, that's kind of the definition of a critical failure and a huge liability.
It absolutely is, and really highlights the critical need for extremely robust testing, validation, and maybe ongoing monitoring across all the specific disease categories a system like this handles. Well, the system might be deliberately tuned to favor safer errors. In some areas, like maybe confusing normal with pneumonia, confusing an urgent risk of sight loss with the routine checkup is categorically unsafe. It suggests either a persistent weakness in the underlying OCT classification model's ability to distinguish DME reliably, or perhaps again, an insufficiently precise instruction prompt guiding the LLM on the absolute critical severity of a DME finding.
It really shows that this LLM architecture, while powerful for interfacing, isn't some kind of magic bullet, is it? It's a sophisticated framework, yes, but it still needs incredibly precise human instruction, especially when it comes to translating a model's output into actual clinical judgment and action.
It absolutely does. You need both an accurate underlying model and accurate instructions for the LLM interpreter. The LLM is clearly excellent at the interpretation part, at generating that conversational tone, making sense of the data. But if the rules governing how it uses the outputs from those specialized models are flawed or ambiguous, it can still result in these critical errors.
Okay. Before we move to the broader implications, we should probably just briefly touch on the appointment stub function. You mentioned it earlier. In the current prototype, the actual scheduling feature is just a placeholder, right?
That's right, yeah. In software terms, it's a dummy function, or a stub. It doesn't actually book anything yet. But its existence within the planned architecture is vital. The design ensures that this same function calling mechanism that selects the diagnostic model and interprets the result can then be easily extended and integrated with real-world external scheduling APIs.
So things like maybe linking directly into Google Calendar or perhaps more specialized electronic health record systems or third-party booking platforms like Wix Booking, which was mentioned as an example.
Exactly. The LLM already does the hard part of determining the type of referral needed, urgent or routine, and the kind of specialist required, like a pulmonologist for the lung issue or an ophthalmologist for the eye condition. All that's technically missing is that final API connection to make the booking autonomously based on those parameters.
And that final integration, if implemented, would turn the system from just being a diagnostic aid into something closer to a fully functional, self-contained medical assistant, at least for these specific pathways.
Precisely. The underlying architecture is designed to be ready for that final step of practical implementation and integration with real-world services.
Okay, let's step back now and try to look at the bigger picture here, the so what, if you will. What does a prototype like Robodoc, even with its current limitations, potentially mean for the future of health informatics? And how does it play into that long-running, sometimes contentious debate about machine versus human judgment in medicine?
Well, that debate itself has got a long history, actually predating modern AI entirely. The source paper references some really seminal work, going back to Paul Meehl in the 1950s, and then more recently, people like Daniel Kahneman, the Nobel laureate. Their research over decades has shown that even simple statistical models, basic algorithms, often outperform human experts in certain specific clinical and predictive scenarios.
Right, the idea that algorithms can be better at some diagnostic or prognostic tasks.
Yes, but I think the key insight that this Robodoc prototype really underscores isn't necessarily about absolute superiority in every case. It's perhaps more about consistency.
Okay, tell us more about the value of consistency, specifically in diagnosis.
Well, Kahneman, in his more recent work, highlights this concept he calls noise. By noise, he means the unwanted, random variability in judgments that should ideally be identical. So, for example, two different doctors might look at the exact same borderline X-ray image and come to slightly different conclusions about what to do next. Or maybe even the same doctor might make a slightly different call on a Monday morning compared to late on a Friday afternoon when they're tired.
Human judgment isn't perfectly stable.
It's inherently variable. Machine learning models, however, once they're trained and deployed, offer highly reproducible, consistent performance. They will give the same output for the same input every single time. Now, they might not outperform the absolute best human expert operating at their peak on a complex case, but they drastically reduce that random variability. The noise that we know contributes significantly to diagnostic error rates across the healthcare system as a whole.
So essentially, we might be trading some potentially brilliant but variable human performance for reliable, predictable, maybe slightly above average machine performance consistently applied.
That's a good way to put it. And the source notes that human performance often degrades as the complexity of information increases, or just the sheer amount of data they had to process. Whereas machine intelligence, particularly these kinds of specialized models, often improves or at least maintains its accuracy with more data, up to a point. And that reliability, that consistency, it translates directly into potential gains in efficiency and significantly cost reduction, which has enormous global implications.
Okay, that brings us nicely to this idea of AI as a service in healthcare.
Exactly. Once these specialized diagnostic models are developed and validated, they are incredibly cheap and easy to distribute globally, almost instantaneously. Think about the marginal cost running that diabetes prediction model using TFJS in someone's web browser. The compute cost is negligible, maybe fractions of a cent per prediction.
Right. Compare that to the cost of getting even a few minutes of a specialist physician's time.
Exactly. Which is scarce, expensive, and very unevenly distributed, especially if you look at rural areas or developing regions around the world. Access is a huge issue.
So a system like Robodoc, acting as a reliable first filter or maybe a diagnostic companion, could potentially drastically reduce the administrative load and maybe even some of the initial diagnostic burden on human professionals, particularly in high-cost or resource-limited environments.
It could make specialized medical knowledge accessible in places and situations where it simply wasn't before due to cost or geography. Now, the author is very clear, and it aligns with the general consensus view in the field right now, that these systems are intended as assistants, not replacements for doctors.
They're tools, not autonomous practitioners.
Precisely. They function best perhaps as a companion tool, handling maybe the initial information gathering, the straightforward pattern recognition, the preliminary triage, which then allows the human doctor to focus their limited time on the more nuanced aspects of the physical exam, understanding the patient's full context, building rapport, discussing complex treatment options.
But we can't just ignore the limitations we saw in the testing phase. What are the general limitations that LLMs, even sophisticated ones like GPT-4, still face when applied in these specialized healthcare settings?
Yeah, the paper and the broader literature it references cite several major ongoing issues. One is degraded performance in edge cases, the rare diseases, the unusual presentations that weren't well represented in the training data. Another is a fundamental lack of true contextual understanding beyond the specific information provided in the prompt. They don't know the patient's history unless told. And then there's the big one, the risk of generating misinformation or outright hallucination, where the LLM confidently provides an answer that is plausible sounding but factually incorrect.
Let's focus on that misinformation risk for a second, because the LLM's greatest strength, its fluency, its ability to argue and generate complex human-like explanations, suddenly becomes a massive liability if the core prediction or function call it made was actually wrong. It can sound incredibly convincing while being dangerously incorrect.
This is an absolutely critical point and a major concern for AI safety in medicine. If the LLM makes a serious triage error, like we saw with the DME case, suggesting a routine referral for an urgent condition. It could then potentially generate an entire, fluent, seemingly logical rationale supporting that terrible decision. And that rationale could easily fool a layperson using the tool, or maybe even an overworked professional glancing at the output quickly.
So what's the mitigation strategy? How does the Robodoc architecture try to address this?
The key mitigation strategy employed here, according to the paper, is quite clever. They deliberately avoid relying on the LLM's vast internal knowledge base for generating the core medical facts or diagnoses.
How does that work in practice? What is the LLM doing then?
The system architecture restricts the LLM primarily to being the conversational interface and the interpreter of the specialized model's outputs. It's not positioned as the source of medical truth itself. It functions more like a highly intelligent computational firewall or translator. It's quite similar, conceptually, to the strategy used by the Wolfram Group with their AI integration.
Okay, so the LLM's job is just to correctly call the highly trained, function-specific medical models, the ones rigorously tested for X-ray analysis or diabetes prediction, and then to translate their raw technical output into understandable language and appropriate actions.
Exactly. The actual medical answers or classifications come from those dedicated, validated models, which are subject to rigorous testing and quality control, not from the general, potentially hallucinatory, vast knowledge embedded within the LLM itself.
That makes the LLM a highly effective message passer and translator, rather than trying to make it an all-knowing medical oracle, which we know is risky. And this ties back into that strategy around accountability and errors, training the system deliberately to favor safer errors.
That seems to be the critical compromise, yes. Since we know that errors are realistically inevitable in any complex system, especially in early versions, the pragmatic approach is to try and design and train the system to err on the side of caution whenever possible. As we discussed, over-referring a non-urgent case as urgent, a false positive, is generally considered preferable from a patient safety standpoint to the reverse, missing an urgent case, a false negative. This approach aims to minimize the risk of serious patient harm, even if it means knowingly generating a higher rate of false positives that the human healthcare system will then need to manage.
Okay, looking ahead now, the modular Lego design promises relatively easy expansion. What specific future directions does the research paper outline for improving or extending Robodoc?
Several key directions are mentioned. First, a really important one is integrating the image and text pathways so they become aware of each other.
What would that look like?
Well, imagine a known diabetic patient uploads an OCT scan showing some retinal changes. The system could potentially automatically cross-reference those eye findings with the physiological data it might have from the text pathway, things like their latest age, BMI, HbA1c levels, to provide a much more holistic diagnosis, risk assessment, and maybe even more tailored management recommendations.
So that moves the system from being just three siloed models operating independently towards becoming a truly unified diagnostic platform where different data types inform each other.
Exactly, much more powerful. They also mentioned plans to explore open source alternatives to the currently used paid OpenAI APIs, maybe looking at models like Google's Gemini or other open LLMs. The goal there would be to potentially reduce the operational costs of running the service and also reduce dependency on a single commercial vendor.
Makes sense from a practical and strategic perspective.
And then there's perhaps the most practically powerful future feature mentioned, leveraging the LLM's increasingly sophisticated file reading capabilities.
You mean the idea of it being able to extract data directly from, say, an uploaded PDF?
Precisely. Imagine instead of the user having to manually type out their age, BMI, and all their recent lab results from a report, they could simply upload a PDF of their latest medical summary or lab report. The LLM would then ideally be able to automatically parse that document, reliably extract all the required physiological parameters, and then feed them into the relevant prediction model, like the diabetes one.
Wow, okay. That would eliminate almost all the remaining user input friction, wouldn't it?
Almost entirely. If they can reliably nail that PDF parsing feature, it could fundamentally change the practical utility and the adoption rate of a system like this. It makes it vastly easier for patients to use.
Well, this has been an incredibly detailed deep dive into how these powerful, specialized computational tools are potentially being freed from their sort of academic cages. I think the core achievement of this Robodoc prototype, as laid out in the paper, is demonstrating a potentially successful and importantly scalable way to connect established, tested machine learning techniques like transfer learning for computer vision with the absolute latest advancements in conversational AI, specifically using LLMs as these intelligent function callers.
Yeah, it really radically simplifies the whole UI/UX paradigm for interacting with these specialized domains. It directly attacks that primary barrier to wider adoption we talked about earlier, the sheer complexity of the traditional interface. And that modular, potentially single-language architecture makes the system highly adaptable and seemingly ready to scale, which could help ensure that valuable specialized medical knowledge isn't just confined to a few experts, but might one day be accessible to many more people through just a simple conversation.
However, we absolutely have to carry the weight of those critical triage errors that surface during testing, particularly that confusion between an urgent, potentially sight-threatening DME condition and a routine referral. It's a stark reminder. The models might offer consistency, they might offer predictability that exceeds human averages in some narrow tasks, but they are clearly not infallible, especially when it comes to nuanced clinical judgment and urgency assessment.
And that leads us, I think, to the crucial final question, the provocative thought to leave listeners with. If systems like Robodoc do become, as seems plausible, maybe even inevitable in areas with the resource constraints, the default first layer of medical assistance globally, and if we deliberately train them, as discussed, to favor safer errors, which often means more over-referrals, more false positives.
Then what practical mechanisms, beyond just hoping for more human supervision, which might not be available, what mechanisms must we implement to ensure that this purposeful influx of safer errors, this intentionally higher rate of false positives generated by the AI, doesn't simply shift the burden, doesn't just overwhelm an already strained human healthcare system, effectively creating a new and potentially even worse bottleneck, this time in human triage capacity, trying to sort through all the AI's cautious referrals.
That is, I think, the critical organizational, systemic, and ethical challenge we face in the next decade as AI moves from prototype to widespread practice in healthcare. How do we manage the predictable flood of false positives generated by these highly conservative AI-based screening and triage tools without completely drowning the very human professionals they were originally intended to assist? The machine becomes predictable, yes, but the human system downstream has finite capacity. Finding that balance is key.
A compelling and absolutely crucial balance to monitor as this technology evolves. Thank you so much for walking us through the architecture, the potential, and the very real challenges highlighted by the test results of this groundbreaking prototype.
Always a pleasure to get into the technical weeds and think through the implications.
And thank you, our listeners, for joining us for the deep dive. We hope this exploration has given you a much deeper understanding of how conversational AI is poised to potentially redefine the very interfaces of specialized science and medicine. We'll see you next time.